Hydrogels and their current applications. Hydrogels are 3D network structures that are created from natural or synthetic polymers. These polymers are hydrophilic, meaning that they hold on to water. This, combined with the porous structure that hydrogels have, means that they have the ability to swell and carry large amounts of water. Hydrogels are an excellent candidate for drug delivery because their polymers are typically non-toxic and non-reactive. They also have good shielding structure, which enables them to protect what they are delivering into the body. For example, semi-permeable hydrogels can protect the cells within it from the outside environment, while simultaneously allowing nutrients to move inside. To stimulate drug release, hydrogels are formulated to be triggered by specific stimuli, such as light, temperature, pH, or electrical signals. An ideal hydrogel would have good permeability, biocompatibility, flexibility, and viscoelasticity. Hydrogels can be administered in a variety of ways. Two of the most common routes are transdermal and oral. One of the most basic examples of hydrogels are topical ones. Topical hydrogel patches can accelerate wound healing by simply maintaining a moist environment on the wound area. They can also deliver drugs to the site of the wound or skin disease. And because hydrogels keep the stratum corneum well hydrated, more of the drug can also be absorbed through the skin and into systemic circulation. For example, silver nanoparticles were put in a hydrogel patch as an antibacterial to improve wound healing. Adhesive hydrogel patches using an antibacterial drug called triclosan have also been used to treat acne vulgaris by targeting the microorganisms that contribute to the development of acne. Topical hydrogels have the potential to treat many other diseases, such as fungal infections. Many antifungal systemic drugs have significant negative side effects, which decrease when used topically. So, a controlled drug release can be reached through the incorporation of antifungal drugs into hydrogel patches. This has the potential to achieve high levels of local drug concentrations while minimizing the drug's presence in systemic circulation. Hydrogels can also be administered through the oral route. Their great biocompatibility and mechanical compliance allows them to act as a non-invasive alternative to gastric implant procedures. But 3 criteria must be met before reaching gastric residency. The hydrogels must have the ability to swell very quickly, swell a lot, and withstand digestive mechanical forces. However, these 3 characteristics are difficult to engineer into a single system. A study conducted by Liu et al. In 2019 designed a pufferfish-inspired hydrogel that was able to hit all 3 requirements. The device was to be taken as a standard pill and swell quickly in the stomach, while also being able to survive digestive forces. The hydrogel was able to remain in the gastric tract for up to 29 days in animal models. It could be used for long-term measurements and monitoring of gastric conditions using mini sensors or cameras, long-sustained drug delivery, and controlling obesity by helping manage satiety through volume exclusion. When the hydrogel is no longer needed, it can shrink and exit the body on demand after the patient takes a biocompatible salt solution. The versatility of the forms and uses of hydrogels give them a lot of potential to be a part of future medical innovations. With growing applications such as tissue engineering and regeneration, treatments for previously incurable diseases may be developed. Special thanks to the Nguyen Lab at UNC Chapel Hill and the Eshelman School of Pharmacy.